Okay, our next topic with respect to the Sun is solar activity, and this will bring us into the idea of magnetic fields. So the Sun is basically a big plasma. We talked about how we've got free electrons, we've got electrons going, attaching themselves to hydrogens and so on. It is a big plasma, and it is spinning. And so essentially what you get is a huge magnetic field, but it gets messed up. But also, the Sun is spinning in such a way that it is called a differential rotation. So the equator goes around in 25 days, but the poles go around in about 30 days. What that means is, let's say you've got a nice, neat dipole. So basically you can think of it as being, it's spinning, you've got all these charges, it's behaving like a coil. It's behaving like an electromagnet. So you've got a magnetic field that's a nice dipole. But now as it spins around, it takes a little more time for this part here to go around than this part, so this gets ahead. After 2 rotations, this is further ahead. After 3 rotations. And as you go on like this, instead of having a nice dipole field, you've now got this toroidal field that's going around like this. It's also getting messy. The field lines are getting so close together that they're starting to bulge out, and this is actually what gives rise to sunspots. And so here what we get is, we get these sunspots, and we can measure the magnetic field, which I'll come back to in a second. We can measure the magnetic field of the sunspots, and we find that they're poles. And what you get is a prominence. So you have field lines, you have magnetic field, you have a south pole and a north pole, and you will have material that is charged following the field lines, and you get these prominences. You'll see that you will always have, if this is the north pole, then the north pole will be the leading pole of the 2 sunspots. So they will come in pairs. Occasionally they migrate towards each other and destroy each other, and so basically you get a reconnection, and then this material will get sent off into space, and that's a flare. So sunspots have a dark region in the center, and then they have a slightly less dark region around the edges. They always appear in pairs, north-south poles. They have very strong magnetic fields, and it's the magnetic field that basically, remember that the energy is flowing as material is flowing. And so if you have a very strong magnetic field, you can inhibit the flow of charged particles, and so the energy doesn't flow, and so you get a cooler area. In fact, they're about 1,000 or so Kelvin cooler than the surrounding surface, and so they're still pretty bright if you could isolate them, if you could mask off the Sun around it, but because the Sun is so bright, they look dark. So we can work out how bright they actually are quite easily. Because the surface just behaves like a black body. So we have the Stefan-Boltzmann law, the flux is proportional to T to the 4. So we know what the temperature is from the color, and so we can work out how bright it is. So it's actually only about 1/3 as bright as the rest of the photosphere. And so what you get is something that looks dark, even though it's actually red. As I said, we get these loops, and then they will come together, and you'll get this material is no longer bound. So at the moment it's bound because it's following the field lines, so there's a sunspot here, material flowing from one pole to the other, and if these two migrate together and the field lines reconnect, this is no longer held by the magnetic field, and it disappears off into space, and that is a flare. Now, it turns out that sunspots have a cycle. So there are periods when you have very few sunspots, and periods where you have a lot. And here you can see the data for the last 150 years or so. This is the average number of sunspots in a year, and you can see it's you've got variations where you've got a lot here and less here, but overall it's a fairly regular cycle. And the cycle is about 11 years. That is, yeah, it's about 11 years. Usually you find them up at this, you start out with them up at this highish latitude, but then they will migrate, and so you'll have them coming closer and closer to the equator, and this is to do with the way that the field lines are wrapping around. And they don't usually get to the equator, they only get to about 10 to 15 degrees, and then they disappear. In fact, when they disappear and you go to a sunspot minimum, what you find is that the north pole of the Sun is now south pole, and vice versa, and so actually what you've got is a 22-year cycle. So it's 11 years from sunspot minimum to sunspot minimum, but 22 years from this being a north pole to it becoming a north pole again. And so here this is showing you what happens if you plot the latitude, so the position and the number as a function of time, and you get this Maunder butterfly diagram. And so you can see that the sunspots start out further away from the equator and tend to get more and more towards the equator, and then they disappear, and then it starts over again. Here you can see this cycle, and so what we're getting is either lots or very few, and so you've got a reversal of polarity here, and then it will reverse polarity again here, and so to get back to the beginning it's here, so this is that 22-year cycle. Now, I said that we would talk about how we know what the magnetic field is, and it has to do with what is called the Zeeman effect. So basically what happens is that, charged particles are affected by magnetic fields. So if you put an atom into a magnetic field, it actually affects the energy levels because it affects the electrons and the protons. So what happens is, instead of having, so for instance, you might have something like this, might be hydrogen going from 2 to 3, it's absorbing a photon, and so you've got this dark line. But what happens is that the magnetic field will actually cause that one or both of those levels to split, so you have more options. And so you get the splitting, and you can see here we've got two lines, and this is a sunspot. And so what you're getting is that in the sunspot you're actually getting more different options, so you get this splitting, and this splitting tells you what the strength of the field is. And because you have more than one line, and they are going to be affected slightly differently, and you have not just hydrogen, you have all sorts of atoms, you can fairly easily get a good grip on how strong the magnetic field is inside of the sunspot. Now, there's a lot of discussion about how the sun and its activity affects the Earth. When there are lots of sunspots, it's pretty active, you get more of these flares, more material gets sent towards us, and then when there are hardly any, they may not affect the Earth at all. But there was a period in the 1600s when there were hardly any sunspots. And remember that the first sunspots were spotted only earlier in the 1600s by Galileo, and there were basically no sunspots in this time. And this was the Little Ice Age in Europe. During this period, the Thames in London froze over. London is never that cold. There's also some evidence from Chinese records that there were higher temperatures during the 11th century and that there were more sunspots. So there's some interest in tracking these things. Now, how do we do this? How do we look at how the climate is changing and whether it correlates with solar cycles? We need to have a long period check on how climate is changing. Well, you have some trees that live thousands of years, and so you can actually use the tree rings and look at, is there a correlation with the 11-year, 22-year cycle? And then also ice cores. You get gases from the atmosphere trapped inside of ice cores, and it does the same thing. So we can actually look and see what those relations look like. And I'm going to finally finish off with the solar wind. Solar wind is what happens outside the corona. So this also affects us in the sense that it's the material that's flowing off the sun and comes towards the Earth. And it's basically a stream of mostly protons, some alpha particles, which are basically helium nuclei, and they're flowing away from the sun in all directions. And in fact, it is the interaction with the solar wind that gives rise to the shape of comets. So we've got a dust and a gas tail. There's actually two tails, and you have radiation pressure. You also have this solar wind that gives rise to the tail from the sun. But basically you've got lots of material up in that hot corona. It's so hot that it can't be held onto, the atmosphere is not retained, and so it's going to flow away. There's also some issues of how the magnetic field may be accelerating material, and that's still an area of current study. The solar wind has huge variations in its speed. It can be moving anything from 300 to 1,000 kilometers per second. And where we are, at 1 AU, it averages about 400 kilometers per second. It's pretty low density. It's only, 700 hydrogen nuclei per centimeter cubed, but that's the average, and it changes hugely depending on whether you've just had a flare and there's a lot of material coming off. And the sun loses a very small amount of mass. So 10 million tons a year sounds like a lot, but it's 10 to the minus 20 solar masses. So even over the age of the sun, its loss to solar wind is negligible, and we really don't need to worry about it. But the solar wind essentially is giving us a bubble in which we live. So you've got the sun, and it's blowing this bubble in space, and then we're moving through space, so you get this bow shock where this bubble of material that's being blown out by the sun is hitting the surrounding material. And so here we have this bow shock, we have interstellar material, and this zone here is the heliopause, and that's actually where the Voyager mission has got to. It's a long way out, but we seem to be detecting evidence of changes in the number of particles that can be attributed to this effect. And so I want to finish with this summary of the layers. So we've got the radius, the temperature, the density, and what defines it, from the core out through the internal region to the surface, through the atmosphere, and into